There are important situations in which you need to use the cylindrical polar coordinates rather than the Cartesian coordinates in order to solve problems with the biharmonic equation involving the Airy stress function. Now, some of these cases are obvious. For example, if you have a circular disk which is thin in the out of plane direction, so you have a circular disk on a flat surface subjected to, say, let's say a load. This kind of a problem is, of course, it has a cylindrical geometry, so it is easier to solve in the r theta coordinate system rather than in the Cartesian coordinate system. But there are other non-obvious cases. For example, you have a half plane. Let's say you have a half plane. So this is your x1, this is your x2, and you have a point load applied here. But this is not a point load, this is a line load. It goes into the plane because this is, let's say, a plane strain situation where the load runs continuously in the z direction. So if you have this, sometimes it is useful to find the stress state close to the in the region close to the load, in which case this may be your r and this may be your theta, and in this coordinate system it is easier to visualize the stress or even calculate the stress. So these are the kinds of problems that we are going to solve with the biharmonic equation in cylindrical polar coordinate system. So in this lecture, what I'm going to do is I'm going to tell you the structure of the solution that you can expect and how to quickly determine that solution. Now we will neglect body forces for the time being, so we know that we have to solve del 4 phi equal to 0. In other words, we will have to find a phi that satisfies this biharmonic equation, and we know already that this del 4 is del square of del square phi. So this is equal to 0 is what we need to solve. And long time back, when we did conversion from Cartesian to cylindrical polar, we had noted that del square of the del square operator in cylindrical polar is this. So operate phi with the del square operator 2 times to get this equation. Now let me erase this. Okay. Now in the Cartesian system, the stresses, remember, were given by sigma 1 equal to del square phi del x2 square, sigma 2 is del square phi del x1 square, and sigma 1 is minus del square phi del x1 del x2. So these were the stress and Airy stress function equations, and corresponding to this you have the similar equations in your cylindrical polar coordinate system, only that now the stress components are called sigma rr, sigma theta theta, and sigma r theta. I hope you know what they are. So if you have a coordinate system with r and theta, sigma rr is this, sigma theta theta is this, and r theta is probably. So this is your sigma r theta. We know this. Okay, right. So now this looks a little bit more formidable than in the Cartesian system. But let us look at it systematically. So in the Cartesian system, what we tried at the beginning was a series solution. We called that a brute force solution, where we broke up phi into a big series containing different powers of x1 and x2. We can do a similar thing here, and the series that we can take, because it has a geometry with r and theta, the series that we can take can be a Fourier series. So this is a kind of series solution that is possible to take. These take care of the angular terms, and these are equations. These are functions that are functions of R only. And if you put this uh, assumption on phi to this equation equal to 0, which is again this, then for both Fn and Gn you will get this set of ordinary differential equations. I've written it for Fn. These are valid for Gn as well. And note that n is an integer, so for different values of n starting from 0 to infinity, you will get a equation each for Fn and Gn. Okay, now these differential equations have, this is a fourth order differential equation, and this has a general solution. If you find that general solution, plug it back to this phi, you get a long series again, and that series is given here. This was given by Mitchell in 1899 and is called the Mitchell solution hence. So in this series, this is the most general series. Once you have assumed the Fourier series as a solution for phi, this is the most general series that can result. However, you can't use this series blindly all the time because of two things. One is that there are situations when R equal to 0 is a part of your domain over which you want the solutions. For example, you take a disk, like I showed, you have a disk on a surface and R equal to 0. R equal to 0 is the center, which is part of your domain. Say it's under some load like this. So R equal to 0 is part of the domain, which means that terms like this, which are undefined at R equal to 0, will not be part of the solution. You should not so much be worried about phi, but from phi we are going to get the sigmas, and then some of these terms will lead to log R kind of terms in the stresses, and those terms will go to infinity as R tends to 0, and those terms which go to infinity, which give stresses that go to infinity as R goes to 0, have to be weeded out from problems like this where R equal to 0 is part of the solution. However, you must remember that if the problem is like this, say the R equal to 0 is not part of the domain, so you have a hole here, you have an annulus basically. So R equal to 0 is not part of the domain. In that case, terms that go to infinity can still be part of the solution, but not in this case. So if you have a situation like this, you have to see which terms in phi lead to terms that are infinite at R equal to 0, and those terms in phi have to be weeded out from the solution. Okay. Now, in these problems also, where R equal to 0 is not part of the domain, if you take a line like this, across this line, you would expect the displacements to be continuous. We have still not learned about how to get the displacements starting from the Airy stress function, but we will learn that in a moment. But we already know that the displacements have to be single valued, which means that terms like theta in the displacement are not allowed, because theta increases by 2 pi every time you go around the origin. So those are typical multiple valued terms that arise in these kinds of solutions, and terms like this, when they arise in the displacements, would give rise to multiple valued displacements and therefore will not be allowed for a problem like this. So those terms also will have to be weeded out from your initial assumption of phi. Okay. Now Mitchell has calculated, given this big series Mitchell has calculated the stress terms that arise from here, which is easy to do because once he has the phi, he just has to do a big integration, big differentiation to calculate these terms, and figure out what are the terms in the stresses. He has also done it for displacements, which we will come to later. But let us see the stress solution first. So the stress solution is summarized in this table. What do you have in this table? So here you have the terms in phi. These terms are these terms here. So these terms one by one are listed in the first column. Then when you take its derivatives and find the stresses from these equations, when you find the stresses from these equations, each of those terms will give rise to a term in the stress which contains r and theta, and those terms are listed in the next three columns. So sigma rr here, sigma r theta, and sigma theta theta here. So these are the terms that arise from the terms, if you include the terms in the Airy stress function, which are given in the first column. Okay, so this is the solution made easy for you, and this is going to help us solve problems, which we will do in the next lecture.